Hello, hello, hello. Can you hear? Hello, 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 Jayla. Hello, Charlie. Can you? Wait, can you? Hello, Juliet. Hello, Vivian. Hello, Alyssa. Good morning, Vivian. All right. Let's. Good morning, Alyssa. Good morning, Noel. Oh, that's okay. Okay. You guys can hear me, right? Okay. Oh. Oh, good morning, Lakshmi. All right. That was fast. How you did that? Okay. Like came on very fast. Okay. Good morning, guys. So good morning, Vivian. Good morning, Alyssa. Good morning, Noel. Good morning, Lakshmi. I know. Okay. All right. Let's just we are going to, and good morning, Charlie, and good morning, Julian. I'm like suddenly concerned about Charlie and Julian. I don't know why. You guys can hear, right? Charlie, you're the you. Well, anyway, okay, okay. What I want to do. Oh, good morning. Good morning. All right, cool. I'm relieved now. All right, now my day can start. Thank you, Charlie. Okay. Good morning, Saad. Okay. You might have quite. What I want to do. I want to go. What I really want to do is finish the problem, or at least the main part of the problem that I was in the middle of Monday. I think it's important. I think it's important to finish this problem. I'm going to sort of dive into it. Then there's a million other things I could do on the exam, obviously, but I think it's best that I answer questions. All right, so I'm just going to get to back. I'm going to use the same sheets that we were using yesterday, just to remind you again. The midterm will be posted this evening, no later than 8:30. It might be a little earlier. If it's a little earlier, that's not meant to freak anybody out. Just I can't promise that it'll be any earlier, but somewhere in the evening it'll be posted. It's due back before 10:50 a.m. this coming Monday. Again, you can do anything you want to do it, but then when you turn it back to Google Classroom, you turn in your own white blank sheets with your name on it, with all the work. You do the best job you can to make it so that I don't have to look at anything else in order to grade your exam, right? Like you make all the questions clear in each question, et cetera, et cetera, et cetera, show all work, et cetera, et cetera. There are more instructions in the Google Classroom. And again, it'll look a lot like the practice exam that we're going over now. And again, one last thing. So I just put my number in the chat again. That once the exam starts, what that's really for, I mean, I'm not going to help people once it starts, but certainly if there's something unclear, or you think there's an error, or or you have a crisis like in your family, and so you think your exam is going to be late or something like that, like I just put my phone number in the chat again. Please do use it, and I would almost encourage it more than email, especially if the rule of thumb is, I mean, identify yourself, of course, but also basically ask a question or make a request or something that takes me less time to respond to than it took you to construct the question. You follow me, right? So don't text me and say, can you help me with problem 3? Like, no. But if you say, wait, are you sure you didn't make a typo in part A of question 2? I don't think the number worked, or something, that's what it's for. Okay, I'm gonna go. And again, please ask me any questions or tell me anything this period. I'm hoping this period makes, the goal of this class period is to leave you with as much calm confidence as possible, not the reverse. that's the goal. So, and I think it will help if I finish at least the problem that we were discussing, which is right here, which is, okay. So I'm gonna switch screens for a second just to remind you exactly where we're at. Just for a second. Right, we are talking. Oh, and let me say also quickly, if you didn't already figure out, like with this problem right here on the screen right now with, and please, maybe someone in the chat, I know I'm talking sort of, please someone in the chat just confirm if you're, just someone just tell me if you, like, if I'm making sense, if you're hearing me basically, but that's chat. Yes, okay, thank you so much. Thank you, Bibi. Okay, yeah. Oh, I got it. Yeah, cool. I've never even seen yeah before. All right, cool. All right, thank you. All right. So one thing, this problem right here in the exam without a paddle, I like gave a brief overview and sort of like a trick about it or something to you guys yesterday in class. Let me be explicit that if you watch the video of the other section, you know, the other video with basically the same name, but it says PM on it rather than AM. It just turns out that I went into far more detail about this problem in the other section. I mean, I practically did it for them. Like I practically did the whole thing for them. So please check out that video if you want more insight about this problem for you. Okay. You know, you still have to understand it and do it in your words on the paper, but I practically did give a whole solution to it so please watch that video if you care. But now going back to, and I'll also say, oh yeah, we did this one, right? We did this one, okay. You should know there's a video where we went over this problem already from last week, right? This one right here, okay. And I this one right here, by the way, if we don't get to today, I mean, I'll try by the end of the period to say tips or techniques, or if you have specific questions, you know, that you want to guide me, I can. But I will say that this one, it may sound very intimidating, but it really is. It's very much like this one. It's very much like Wile E. Coyote, and it's also very much like Lab 4, which I believe you have at least started, if not done. I mean, and we definitely did post a video about Lab 4, whether you did it or not. A video about like something going off a table and landing on the floor. In effect, that's what this problem is. It may not sound that way, but use your notes from that to do this one. Anyway. Which leaves then that I think really the hardest problem left in the exam is this one here, free float. That's what we were starting to do yesterday, right? And what we're up, okay, and again, stop me if I'm jumping around or whatever, but the key, the sort of centerpiece of this whole problem of free float is part D, right? D is the purpose of the whole thing. D, and that's where I'm going to go back. I'm going to switch screens again in a second and go back to solving that. But D is asking from the perspective of the water, at what velocity is the riverbank moving? Okay, let's just back up for a second and think about what that question means. First of all, this is really probing. You see, all of this stuff is really forcing us to mathematically embrace and deploy and use Galileo's principle of relativity. This all goes back to the whole train of thought thing from the first week of school, of the class. And Galileo's principle of relativity may have, for a while, seemed very sort of abstract and philosophical and like detached from math. But here we're really seeing how it is really mathematical and it really becomes concrete. And so, and you really have to step back and sort of, it's more about believing it and conceptually getting it in your mind than anything that's mathematically hard. I mean, it's actually there to make the math easier. So what am I saying? I'm saying question D, even what is it asking? Okay, it's asking from the perspective of the water, at what velocity is the riverbank moving? First of all, let me tell you, you could put that a number of different ways in your mind and they're all synonymous. Like that's exactly equivalent to asking at what velocity is the riverbank moving from the perspective of the water? Like, first of all, don't be thrown by the order of the words. You could switch the order around and it still means the same thing. It's asked, another way to put it is, what is the velocity of the riverbank in the frame of reference of the water? That's another exactly equivalent way. Like every time I've ever said reference frame or frame of reference, that means the same thing as from the perspective of. Or another way to put it is, what is the velocity of the riverbank relative to the water? That's literally equivalent to what that question's asking. Or you can switch the order around and say, relative to the water, what is the velocity of the riverbank, right? That's what it's asking. It's asking how fast is the riverbank, how fast and in what direction is the riverbank going compared to the water? That is what it's asking. Now, okay, all those things are equivalent. Put another way, it's asking, what is V sub R W? R meaning riverbank, W meaning water. It's literally asking, what is riverbank doing compared to water? Now, first of all, you might even say to yourself, that's a crazy question. Like, what? He's asking how fast the riverbank is moving? Like, what? You got to understand that everything is moving compared to nothing has an absolute velocity, nor is anything absolutely stationary, right? The velocity of anything is always like relative to something else. So it's like saying, what is the velocity of the earth relative to the sun? Or what is the velocity of the sun relative to the earth? Everything has a velocity compared to, right? So put another way, if it's you, I mean, if you're the water, you see the riverbank moving past you. And why is that? Well, for the same reason that if you're the riverbank, you see the water moving past you. It's that same equivalent relationship. And neither one of them might be easier for you to picture than the other. It might even, for some of you, might be easier to believe. Some of you might even be thinking, wait, what? Okay, so he's just talking about, he's saying because the water is moving past the shore, I guess he's doing that weird, annoying physics thing of saying, well, we might as well look at it as the shore moving past the river. Well, yes, that is what I'm doing. I mean, that's true. I'm saying if you can picture the fact that the water is moving past the riverbank, then I'm saying you can just as easily talk about it as the riverbank moving past the water. Now, I'm also really trying to get you to see that neither one is actually more true than the other. If you could picture one, you should be able to picture the other, and you really should get it in your head that neither one is more correct. It's not like the riverbank is actually sitting still and the water's going past it. It's not. The riverbank is part of an earth that's actually moving past the sun, or is actually sitting still relative to it, blah, 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 blah. Like there's no actually about it. There's all comparison. However, again, if I'm asking here, at what velocity is the riverbank moving relative to the water? Certainly what is true is I'm in effect asking what's the current. I am asking us ultimately to figure out, I mean, if ultimately the water is going down past, going south past the riverbank at 5 miles an hour, like if that turns out, if that's what you can picture, if you can ultimately picture that the current is going 5 miles per hour south past the riverbank, then the answer to this question will be that the riverbank is moving north at 5 miles an hour past the water. Like it is true that that's the relationship I'm asking for. Okay. Now, how are we going to get it? So we're asking about the water riverbank relationship. That is, we're going to get it from the givens that we have, which are not that. The givens that we have are how fast the boat is going relative to the water and how fast a boat and in a certain direction. And we also have a given of how fast the boat is going relative to the riverbank. My claim is we could put those together to figure out what, like we have 3 objects here. We have boat, riverbank, and water. If we know any 2 relationships, we can figure out the third. That's what's going to happen here. And I'm going to switch screens in this. Okay. But specifically, I'm saying it's like saying, if you know how fast you're going relative to an escalator, and if you know how fast the escalator is going relative to the mall, then you can figure out how fast you're going relative to the mall. But also, right? That's so I'm talking about that VAC equals VAB plus VBC, that concept, which is so, I think all of you agree with that concept, when it's in one dimension and it's simple and like some of the numbers are zero. Like everybody uses this concept every day when they ride a subway or they ride an escalator. We're here in physics just saying if you believe it, when it's in one dimension and when there's zeros, we're saying it's really still universally true, even when problems get complicated. So similarly, we're saying boat relative to water plus water relative to riverbank equals boat relative to riverbank. And that can be re-scrambled and rearranged to suit our needs. And that's exactly what I'm about to do when I switch screens. But I'm saying, right, again, if I know that me relative to escalator plus escalator relative to mall equals me relative to mall, then similarly here, what I know is boat relative to water plus water relative to riverbank equals boat relative to riverbank. Now, and here the knowns we happen to have are boat and water and boat and riverbank. So we're going to figure out water and riverbank. That's what's going on. Okay. Now it's just a question of doing the math. Let me, or the computation. Let me switch the screens and go back to where we were. Pardon me. Okay, right. Okay. So here, and pardon me for one second. Also, Professor Walters is actually calling. He's probably calling about the exam. Okay. So what do I have written here on the page? Wait, what? Yeah. Notice what I have written here. This is, let me just try to modify this. Like, in fact, let me add a page. Excuse me. I'm going to add a page and insert it right here. Like, meaning, okay. Like, let's say I'm doing the exam, like say I'm you and I'm handing the exam and I'm solving this problem. And sorry, and what I'm on again is this is part, I'm trying to solve part D of part 4. Okay. I assume I've already drawn a diagram. I've given the facts, like, and I wrote down what is the question, steps 1 and 2 of my problem solving method. Now, just to be as clear as I can, step 3 of the problem solving method that we always do is GDP, general definitions and principles. I'm writing down this general definition and principle. VAC equals VAB plus VBC. That's Galileo's principle. It's form number 4. And the idea there, it's general in the sense that for any 3 objects, this concept of velocity applies for any 3 objects, A, B, and C. Now, in the case here, our 3 objects, we've already said, are boat, river, bank, and water. And we've already given them initials, like on a prior page from Latin. Again, watch the video if you're just tuning in now. But we've already said, like, let the B, capital B equal boat, let R equal riverbank, let W equal water. So the way this general principle would apply to those initials, right? That would mean, for example, boat is to riverbank as I want you to notice, I did this already 2 days ago, but I'm doing a little bit slower now just to make clear. Notice I'm just taking the three objects that we have, boat, river, and water, and I'm arranging them in the same kind of sequence as I did with the letters A, B, and C. Like I am writing, this is a real example of what we were saying right in the first week of school. I'm writing something down that's true, and then next I'm going to contort it and rearrange it to make it relevant. I'm not first writing down something that's relevant and then trying to squeeze it into making it true. What I mean by that really is I'm just writing VBR equals VBW plus VWR because that works, because I've put the letters in the correct sequence, the same, I've arranged them in the same pattern as the A, B, and C. Like the concept is I can always add the velocity of me relative to you to the velocity of you relative to a third thing, and that will give me the velocity of me relative to the third thing. Like that's the concept here, and I'm writing it down. In other words, I haven't yet taken into account literally exactly what my knowns are and what the question's actually asking. I'm just writing down a true relationship among the boat, water, and riverbank, okay? So that's like my GDP. Then, and I certainly haven't put any number, I'm like far from putting numbers in yet, right? Then I'm going to now look at this problem, and this is where we were sort of yesterday. The problem is ultimately asking, the question D is asking, what is the velocity of the riverbank relative to the water, right? That's what question D is asking. That's what was on the screen a second ago. It's asking about W and R. Technically, it's asking what's, well, I'll even say, okay, the question. Right? So I'm going to first rearrange this true statement to make it a little bit more designed for what it is I'm looking for. Again, this is what I just did right at the end of yesterday, but I'm trying to make clear. In other words, well, the question, sorry. It's actually, sorry, the question is actually asking about VRW, riverbank to water. Like order does matter here. So I could say something like, so I'm taking the true statement above and rearranging it to solve, to isolate W and R, right? I'm just like doing math. I'm subtracting VBW from both sides of the top equation. And then I'm saying, before I go, okay, so I'm saying, well, according to the sequence of letters, like VWR will equal VBR minus VBW. Like if I want to get the relationship between the water and the riverbank, I'm going to subtract ultimately the boat to the riverbank minus the boat to the water, like just according to the logic of relativity. And I'm noting also that when I do that, when I subtract, I'm going to get VWR. The question's ultimately asking for VRW. So whatever answer I get for VWR, I'm ultimately going to have to negate to get the final answer to the question. So you could say, and as usual, I'm postponing the numbers. I'm really trying to do the concepts first, and then I'll do the numbers. And there's many, many ways to do this. I mean, there really are, but they all have to be consistent with what I'm doing here. Hold on. Okay, I'm about to run the numbers. I mean, do the numbers, but just again, to just try to be clear as possible. Remember, the question is asking, and again, this is the hardest. This part D is sort of the hardest question of this problem, and I think the problem is probably the hardest problem in the exam. So that's why we're spending this time on it. But the problem is ultimately asking, what is the velocity of the riverbank relative to the water? That is VRW. That's what I'm looking for. So I've done a little bit of physics and algebra to set up an equation to solve for the thing I'm looking for, VRW. And I've got it written in terms of knowns, like what's given, the knowns of the problem, if I'm not mistaken, are velocity of the boat relative to the water and the velocity of the boat relative to the riverbank. That's what was given. In fact, let me check that that's actually true. Boat relative to the water and the boat. Yeah, right. Yeah. So what I have here now is a statement of physics, or a statement that looks like algebraic, that relates the two knowns, velocity of boat relative to water and velocity of boat relative to riverbank. It relates them together to get the velocity of the river relative to the water. I've now set up and I'm ready to go. Okay. It's just going to be a matter of math now. So you might even think, okay, well, the two knowns, you might think, okay, velocity of boat relative to water is 12. And the velocity of boat relative to the riverbank is 10, you might think. So now don't you just subtract and say 12 minus 10 is 2 and you're done? No, because these two velocities are in two different directions. They're in two-dimensional space. They're going at two different angles. So in order to subtract these two velocities, what we're really doing is subtracting vectors. We have to take into account their two-dimensional vector nature. We have to realize that we're really doing two one-dimensional subtraction problems simultaneously yet independently, rather than attempting to do. That's what we're really doing here. Is we have two one-dimensional subtraction problems that we're going to do independently yet simultaneously. In other words, we're going to have to break up these vectors into components and make a chart and subtract their components. That's what I was starting to do Monday. That's what I'm going to do now. But also I want to follow the instructions of the exam closely. Like you could tell that D is a big deal question because it then says 3 and 4. First, it tells you to find the answer graphically by drawing vector arrows, more or less to scale. And that's to give you a sense of what kind of answer we're talking about and what's happening. And then it says to find an exact numerical answer. So let me do that right now. Like D. So I'm going to draw a diagram of what's going on with these vectors. And then I'm going to get, so I'm still sort of postponing that page. So. And by the way, I don't know why it's called D3 and D4. That's just a misprint. I mean, there's no reason it should be called D1 and D2. I apologize, but just for whatever reason, it's called D3. So. Okay. I'm about to make a diagram. I'm writing this note to you guys. I mean, I'm not saying that you as a student would have to say what I just wrote here, but I'm saying, vectors vector quantities with magnitude and direction are denoted with arrows. The size of the arrow represents the magnitude, the size of the vector, and the orientation of the arrow, the tip and the tail, signify the direction of the vector quantity. Whenever we place two arrows tip to tail, that means the vectors are being added. This is how vector computations work. If two arrows are placed tip to tail, that's just like what we did in the video last week for adding displacement vectors. We place them tip to tail, which I think is intuitive, but that is a rule that you can rely on for all time. I'm saying that here explicitly. So that means if arrows are placed not tip to tail, they're being subtracted. If you see what you'll see what I mean. Okay, so we have the two vectors we have here. Oh wait, sorry, I'm just going back and forth between. Okay, we have. Yeah, wait, sorry, it's correct, but I want to give myself more room. Sorry. Okay, this is essentially the diagram that 3 is asking for. It's a diagram that shows us what's happening and shows us what the answer will look like and how to picture it. It doesn't get us the answer. Okay, what it's saying is it's saying VBR plus V. Notice VBR and VRW are drawn tip to tail, right? The tail of VRW is at the tip of VBR. It's saying VBR plus VRW equals VBW. Or put another way, that VBR minus VBW equals VRW. It's putting the three vectors together in a way that shows, it gives us a sense of what we should picture our answer to be in the end. Our answer should be something that is roughly as long as VRW and points in the direction of VRW. So it's a graphic representation of what's happening with these arrows. Now I'm going to find the actual numerical answer. I'm going to do the computation. we're going to do the exact same thing that we did with displacement vectors last week. We're going to zoom in on each individual vector that's being added or subtracted. We're going to zoom in on it and break it up into its component, its constituent parts. We're going to change each two-dimensional vector into two simultaneous but independent one-dimensional vectors. This is what I mean. Okay, this is VRW, right? The velocity of the, oh, sorry. This is VBW, the velocity of the boat relative to the water. It's 12 meters per second at 30 degrees south of east, right? That's individually what the boat is doing relative to the water. What I do is I divide that into components. I say, that anything that's heading southeast is really heading some amount east, while at the same time, but independently, it's heading some amount south, right? And this is a right triangle. Every vector that I ever look at, I can always break up into its own little. Every individual vector is its own hypotenuse of its own little individual right triangle. The legs are the X and Y axes. From SOHCAHTOA right now, I'm saying, I'm saying like cosine of 30 equals adjacent over hypotenuse, therefore adjacent equals cosine times hypotenuse. That always works. And same thing with the other. Well, I think you. Okay. And cosine of 30 is 0.866 times 12 is whatever it is. Okay, so all I've done here is just broken up one velocity vector and gotten its components. I'm saying that if you're going 12 meters per second at 30 degrees to the southeast, then you're actually going 6 meters per second to the south, while you go 10.4 meters per second to the east at that instant. Okay, that's what we're saying. Keep that in my brain. Go to the next page. And I'll look at and zoom in on the other component, the other velocity vector now. Sorry, this one is going, this one, B R is going 10 meters per second at 45 degrees northwest, right? So, and north of west, right? And by the way, all of this is assuming, and I should have made this, I did make this clear 2 days ago, but all of this is assuming right? So that's, so when I see it, when I hear, when I'm told that this vector is at 45 degrees northwest, what that means to me is it's 45 degrees north of the west of west, right? So now I break this up. So that's how I figured out that angle. So now I break this, I'm getting the components of this. Right, the exact same routine. Like I necessarily have a right triangle here. Like again, notice I'm not relating the two vectors to each other. Please notice this, and this is called the component method of adding or subtracting vectors. It's what we'll do with all vectors for all time. We did it with displacement vectors last week, and in principle, that's what you were really doing, whether you knew it or not. In lab 3, it's when you put arrows together and you put them tip to tail, and then you realize that those arrows really are hypotenuses of little mini right triangles. That's called getting components of vectors, and it's the way that you add or subtract vectors of all kinds for the rest of physics. But notice the whole key to the method, and please notice the key to the method is that no matter how many vectors I'm adding or subtracting together, and no matter what those vectors mean, I take each one individually first and break it apart into its own components. When you really realize that that's what I'm doing, the whole thing is much easier than it looks, perhaps. We're not putting vectors together and looking for right triangles or having complicated triangles and trying to negotiate like law of cosines or something like that. I'm just taking each individual vector and saying each individual vector is a hypotenuse of its own little right triangle, because each individual vector is doing something like northeast or southwest or whatever. That means it's going some amount north and some amount west, and it's those amounts that I'm using SOHCAHTOA or trig to figure out. Okay, so in this triangle here, in other words, I'm saying this is, so Vx for this is like VBR sub x is 10 cosine 45, and Vy for this one is 10 sine 45, right? In other words, hypotenuse times cosine equals adjacent, hypotenuse times sine equals opposite. So now I can do those numbers on a calculator. Now, what I've done now is broken up the individual vectors now into individual components. Now I'm going to put those components together. I'm going to add or subtract, as in this case, subtract the vectors according to the chart I made a number of pages ago. Okay, this one. I'm making a chart. What I'm really trying to say here is what we're doing is we're subtracting VW from VBR. That's all we're doing is subtracting one vector from another. But we're subtracting one two-dimensional vector from another two-dimensional vector. The only way to do that is to subtract the individual components. It's like, it's again, the subtraction problem we're doing is really two simultaneous but independent one-dimensional subtractions. It's just like lab 3 again, where it's like, if I walk like this and then I walk like this, that's really like first walking some amount this way and then some amount this way and then walking some amount that way. X's can add and subtract to X's, Y's can add and subtract to Y's, but the two can't communicate directly with each other. So we're just making a tally chart of what's happening in the X and Y axes, right? We got all the numbers to fill in this chart. Let's just look at the numbers we got. Like VBR, we got that for VBR, for VBR, we got the number 7.07 and 7.07. In the X direction, VBR takes a 7.07 meters per second to the west, right? Like, look at my picture here. It's going to the left, and look at my diagram below. Like, look at my legend or my coordinate system. Apparently VBR is taking a 7.07 meters per second to the west. So I'm going to make that a negative. Right? And VBR is also taking a 7.07 meters per second to the north. North is positive, so I put positive. Right? I'm just filling in the numbers into my chart. Then VBW took us 10.4 meters per second to the east. That's positive, to the east. So I put 10.4. And it took us a certain amount to the south, right? 6 meters per second to the south. So that's negative. So I put in -6. You see what I'm saying? Like, I'm just making a chart here, and I'm just putting in the components from the vectors into the chart, but I'm paying attention to positives and negatives. Anything that goes to the north for the y-axis is positive. Anything that goes to the east for the x-axis is positive. And I'm keeping the two axes separate. That's really the principle of the whole thing, that we've learned everything we need to learn about physics in one dimension. When physics is happening in a higher dimension, we just do physics twice, is really what, and we keep the two dimensions separate because the laws of physics hold in all inertial reference frames, in all coordinate systems. Each axis is like its own little coordinate system with its own little rules of physics going on. All right, so we're just about done. These are the numbers. We're being asked to subtract. Like, we did the physics at first. We arranged the equation to figure out that we've got to subtract the bottom from the top. So it's -7.07 minus 10.4. That makes negative, I believe. Yeah, that makes negative 18. Well, I better do it, but 18.1 or something. Or 17. God, I am tired. All right, sorry. I'm always rounding, and you don't have to worry too. I'm being conscious, but not overly rigid about significant digits. And then I'm subtracting. Everything here is a subtraction problem. Again, how do I know it's subtraction? Because that's the little physics work I did at the beginning of the problem when I rearranged VAB plus VBC equals VAC. All right, so that was 7 minus, and so this is subtraction. So it's right. It's 7.07 minus -7 makes positive 1307. Right now we're almost done. and I will stop and see if there's questions. It's like we're almost done. But so what does this mean? Like we're not done, but we're almost done. It means at the end of the day, like what we just got down here, what we just got is what we're looking for. We're looking for V. This is going to be V. V. Sorry, one thing. Sorry, I am really tired. I keep getting confused what the question is. Hold on. I don't know if I did. I may have done this. Hold on one second. We decided. We want. We want VRW. PW minus PR. Sorry. Sorry, I did it. My bad. I don't want to, since you're going to look at this later and study and everything, hold on. I did it upside down. I double psyched myself. Let me, bear with me for a second. I'm sorry. Okay, sorry. After putting in all that work into getting the order right, I do apologize. I put the numbers in the chart in the wrong order, and I want to, before I go any further, I don't want to confuse you any further. And if that did confuse you, I apologize. So it's all the same numbers and everything I said. It's just putting them in the correct order now. So my apologies, 10.4 minus negative 7.07 is the same thing as 10.4 plus 7. So we get 17.5. And negative 6 minus 7 is negative. So it's the same. So say, okay. So sorry, for anybody who's, so I just flipped, I put the numbers in the wrong order and now I put them in the correct order. And what we get at the end is the answer we're looking for, but we're almost done. We're not quite done. Remember, the whole time what we're looking for is the velocity of the riverbank relative to the water. Well, we seem to have two numbers here representing the velocity of the riverbank relative to the water. What do those two numbers mean? Well, that's the x component and the y component of the velocity of the riverbank relative to the water, meaning we now have two legs of a final Pythagorean triangle that we can put back. In other words, we have the two separate, the two independent but simultaneous one-dimensional pieces of our final answer. Our final answer is sorry. Notice what I'm doing. Sloppily, but carefully. I'm taking the 17.5, like I'm looking at the chart. 17.5 was the x component of the total final answer for VRW. It's 17.5 positive, meaning 17.5 to the east. So I drew an arrow pointing from tail to tip going to the east. Then at the tip of that arrow, I started an arrow going down to the south because the y component of this final answer was negative. So I'm putting x together with a y, adding them tip to tail and saying our final answer is this right here. This is our final answer for VRW. This is a right angle here. This angle, I don't know. This length, I don't know. That's what I'm going to get for my final answer, meaning so, okay, so the final speed, the speed of, and again, this is a bit of work, right? But again, also just to be clear, I think this is the most work of any part of any problem of the whole exam. That's why I'm doing it here. And I think that if you stare at it over over the next 5 days, you'll really see why all the pieces make sense. And again, nothing else in the exam is quite this involved. But what are we saying? We're saying we wanted to know what's the velocity of the riverbank relative to the water. Well, it is like any vector, it's the sum of its x component and its y component. In other words, how fast is the river flowing relative to the water? Evidently, it's flowing around 21.9 meters per second. Where did I get 21 point? I'm saying this number right here. Where did I get that? I got it from the square root of the sum of the squares of 17.5 and 13.1. So I'm saying the final answer is the Pythagorean sum of those two legs. And what's the direction of this water flowing? It's whatever this direction of theta is. I mean, the direction of this water flow is that angle theta. How can I get that angle theta? I do SOHCAHTOA. I could do any number of SOHCAHTOA things. I think the most straightforward thing to do is tangent of theta equals opposite over adjacent, right? Tangent equals 13.1 over 17.5. In other words, theta equals the inverse tan, the arctan, the tan to the -1 on your calculator of 13.1 over 17.5. So theta equals approximately, and where am I getting 13.1 and 17.5? Those are those legs. And where did I get those legs? I tallied up the legs from the other two vectors. All I'm doing is I'm adding two legs of two vectors in one side of a chart and two legs of two vectors in another side of the chart, and then putting those answers together. In order to add two vectors together, we're breaking apart the vectors into x and y pieces and adding those individual pieces, getting totals, and then putting them back together into one big vector. That's what we're doing. We're saying that one two-dimensional problem is really two one-dimensional problems happening simultaneously yet independently. And the problem here happens to be subtraction. It could have been addition. And the problem has to do with velocities. They could have been displacements. We're just saying that quantities, when you want to add or subtract them up, you've got to do it one dimension at a time. That's what all of this trig and all of this like nonsense math, it's not nonsense, but it is all about, really. Okay. So right now I'm just getting that final angle. It's the arctan of 13.1 divided by 17.5, the arctan of that. So like 36.8. Okay. And now look, I'm going to write the final answer on the next page to try to be as clear. I know this has been a little bit eek. But look at that pic. So, okay, well, here's my final answer. What is this called? What's the problem called again? Free float. couple of quick things. Okay, we have 7 minutes. This is the final answer to 3. I think, again, I think this is the hardest question in the whole exam. So, you know, if you're, and I think you might want to think about this over the next 5 days, or et cetera, or you like talk about it with your friends. Please understand, I'm intentionally doing the hardest thing here to try to help you. If it's a little bit stressful, I do apologize for that, but that's why we're doing this together right here. This is the final answer. Notice that I'm being asked for a velocity. I'm being asked for the velocity of the riverbank relative to the water. Velocity has is a vector quantity. It has magnitude and direction. To provide a velocity, I must provide 2 pieces of information: the actual speed in meters per second and the direction. And now the direction, this is a 2-dimensional problem. So the direction is an angle and points of the compass. It's not sufficient just to say negative or positive once we're in a plane. We have an angle here that we solved for of 36.8 degrees. And look at my picture. If I've been careful about directions, if I've been careful about positives and negatives at each step of the way along, if I've been careful about keeping track of positives and negatives on each individual axis along each step of the way, then, and if I've placed my arrows in the appropriate directions, then my picture is not an accident. It is deliberately showing me an angle that is opening to the south under the east. Like that angle is pointing south of east, just in the picture, because my final answers are going east and south. And how did I know that my final answers were going east and south? Because the horizontal one had a positive sign and the vertical one had a negative sign, right? And how did I know that? Because I put in positive signs and negative signs accordingly from my pictures. Okay, so to add or subtract velocity vectors has 2 moments in it. One, you have to realize that VAB plus VBC equals VAC, and you have to do the physics of that and arrange the letters according to match the problem. And then you've got to break up the velocity vectors into components in this way and get the final answer. This is the final answer to that. I think for the sake of closure, sorry, so this is the final answer to that thick problem. Again, that's as thick as it gets. And obviously, like, sit with this, debate with your friends, like watch the videos, like in all seriousness, like it is, every little piece should ultimately make sense, but it is a lot of pieces together without a doubt. And you want to let them marinate. You want to practice it, like do a rough draft or whatever. But for the sake of closure, wait, so we have 4 minutes. I think, wait a minute, just let's see one thing. I want to see if there's any other question. Hold on, I think I could do E, just to give you an example of what I'm asking about in E bird's eye. They're not hard ones, you know what I'm, if I want bird's eye diagrams, like, okay, so boat frame. From the boat frame of reference, like, so that means what if, from the boat frame of reference, we have water. And we have okay, I'm just going to say this because we have 2 minutes. Here, it asks for 3 bird's eye views in part E. I'm just giving you one here as an example. Once you see one, I think you can do the other. I'm giving you all the velocity. So it says 3 bird's eye views, like one from the boat's frame of reference, one from the waters, one from the riverbanks. Here's the boat frame of reference. What did I do to get the boat's frame of reference? I looked at all velocities according to the boat. Well, how do I know them? Well, I looked at the problem. The problem told me that relative to the water, the boat goes 12 at 30 degrees southeast. This goes back to the first couple of questions in the problem. If the boat relative to the water is going at 30 degrees southeast, then the water relative to the boat is going 30 degrees northwest, right? Like water relative to boat is the opposite of boat relative to water. And similarly, if the boat going relative to the riverbank was going at 10 meters per second at 45 degrees northwest, then the riverbank relative to the boat is doing the opposite of that. It's going 10 meters per second at 45 degrees southeast. So this, what I just drew right here, are the 2 vectors of what this is, the vectors of the water and the riverbank, both from perspective of the boat. It's what the boat sees is going on. And I could do the same thing for the other 2. You're just doing it the same way. Okay. We have 1 minute. I will hang for a couple minutes if there's any other questions, but are there any? I mean, obviously I wish you the best of everything. You should work together. Please work together and help each other out. And but the thing will be posted tonight. So are there any questions? And I will hang out here for a minute if there's any like private questions or anything. But I mean, if not, have a good, okay, thank you. Thank you. Have a good day. But thank you. Have a great day. Have a great day. Okay, thank you. Thank you.